Make sure you have your notes outline out, and let's get started. All right, this is all about energy. And energy is simply the ability to do work or produce heat with which you can do work. There's two main forms. It's potential, it's due to the composition or position of an object, and kinetic, which is the energy of motion. If you think about water behind a dam, you can see there's potential and kinetic energy. Take a moment to determine where each is represented in this picture. All right, so got lots of running water here. That would be the kinetic energy. As the water flows through the turbines, it turns the turbines, which generate electricity. Now behind the dam, you have the potential energy of the water that is held higher than the stream, and that gives it the energy of position so that the gravity can pull it down when needed and get the energy out of it, change it from potential to kinetic. That's kind of a review from integrated science. Now in chemistry, we think about both kinetic and potential energy, but it's a little bit more challenging to tease out what's what because you're talking about atoms and molecules and bonds. So the kinetic energy is just related to the temperature. As we've talked about in the kinetic molecular theory unit, as temperature goes up, the particles get more kinetic energy. Okay, everybody, time for a photo. Say hi to Mr. Clark. All right. Back. Kinetic energy is affected by temperature and only temperature. As long as it's the same molecule, that's the only thing that impacts it. Kinetic energy mathematically is 1/2 mv squared, m being the mass. So obviously if the mass of the compound changes, that changes its kinetic energy, but the velocity changes based on the temperature. All right, then there's the potential energy, and this is the complicated part. It depends on the type of atoms, the number and type of bonds, and the way they're arranged, because all of these things impact the potential for them to cause a chemical reaction, be a part of a chemical reaction. We'll be teasing all of that out as we go through the unit. All right. Big review. The law of conservation energy states that in any chemical reaction or physical process, energy can be converted from one form to another, but neither created or destroyed. Can't gain or lose any energy. It's always accountable. And the wording is important here because this says chemical reaction or physical process, which means nuclear radioactive processes are different. And so they're not included in that law. All right. The energy stored in a substance because of its composition is called the chemical potential energy. It's not something we can see or predict by looking at something, but as we study how it behaves chemically, we can understand something about its chemical potential energy. This is one of the things you have to measure and actually experiment with to know what's there. For instance, you see a piece of wood, you see a piece of coal, you might not know that they have quite different potential energies. They both have the potential to release a lot of energy when combusted, but the coal has a much higher potential for releasing heat, is much more energy dense than the wood. Heat is how we measure that energy that is released or absorbed. Heat uses the symbol Q when you're talking about how it's quantified in a lab, and it's the energy that's in a process of flowing from a warm object to a cool object. We talked about this when we did the ice cream. The energy went from the ice cream mixture into the ice, not not the opposite way around. Heat flows because heat is that energy. Cold is that absence of the energy. Okay, to measure heat, measure that Q, we need a unit. You probably have used the unit of calories, which is for the metric system, the amount of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius, and it's often used to measure the amount of heat chemical potential in food. In the chemistry class, we typically use the energy unit of joules. And a joule is equivalent to 0.2390 calories, or easier to use is that 1 calorie equals 4.184 joules. So that 4.184 joules is how much energy it takes also for 1 gram of water to raise 1 degree Celsius. Okay, so here's a little chart showing the conversions because you'll probably want to practice that. I do want to note here that there's a unit here, calorie with a capital C, a capital C, and then some with lowercase c's. There's a difference. A calorie is that amount of energy to raise 1 gram of water by 1 degree Celsius. A capital C calorie is the amount of energy that we talk about as a food calorie. So if you're talking about 200 calories in your Snickers bar, that's 200 times 1,000, 200,000 little calories. That's a lot of energy in that Snickers bar. All right, so this ratio of mass to energy per degree Celsius, energy per mass in degrees Celsius is called the specific heat. It's a way of comparing substances and how much heat it needs to absorb or release in order to change its temperature. So the bigger the heat capacity, the harder it is to heat something up and the longer it takes to cool something down. So water is 1 calorie per gram or 4,186 joules per kilogram. All the way down to metals, which have very small heat capacities. If you think about it, it makes sense that the metals that transmit heat well have a low capacity for heat. They heat up and cool down easily. They transfer it well. Whereas water, air, soil, they're more able to resist the change when things are heated up. Okay. So on to the calculations. The heat absorbed or released by a substance during a change in temperature depends on its specific heat, the mass of the substance, and the amount of the temperature change. So, for instance, if you're trying to heat up some water to make a cup of tea, you would know its specific heat. You would have a certain mass, maybe 250 grams or something like that, and you'd want a temperature change of maybe 20 degrees Celsius to 80 or 90 degrees Celsius. And you could calculate the heat that would take. If, for instance, if you wanted to heat up water for a bathtub, it'd be very similar, except the mass would be much, much larger, and therefore it would require a lot more heat. Okay, here's the equation. You hopefully use this a little bit in integrated science. Q equals C is heat capacity, M is mass, and delta T is change in temperature. Okay, just went through that. Now, if we wanted to use some information like that, we could find out something specific heat if we didn't know what the substance was. So, for instance, if you're constructing a bridge or a skyscraper, you have to leave a gap because metals expand and contract with the change in temperature. So let's say you have a sample of iron, 10 grams of mass, and it changed temperature from 50.4 degrees Celsius to 25 degrees Celsius with a release of 114 joules. What is the specific heat? Well, you've got your Q, your 114 joules, and that equals Your specific heat you don't know, that's your unknown. You've got 10 grams. And you do the change in temperature, usually do final minus initial. In this case, it's releasing heat. The temperature changes 25.4 degrees Celsius. It's actually a negative, and with the release of heat, the joules is negative. Release is always negative, and you should find that specific heat of iron is, oh, 0.449 joules per gram degree Celsius. And you could use the chart and identify that as iron. All right. In doing these kinds of experiments in the lab, you have to use something that's insulating so that the outside air temperature doesn't impact the experiment itself. So it's something called a calorimeter. And it usually looks something like this, with a chamber where the chemistry is going on, or the physical change, an air gap, which is an insulator, and some sort of lid that keeps heat in from above. So let's say we have a calorimeter, and we can use a cheap version by using styrofoam cups. If you have 125 grams of water, let's keep track of what we know, into a foam cup, and that its initial temperature is 25.6 degrees Celsius. And you add to that a 50-gram sample of an unknown metal, which was at 115 degrees Celsius. You put that in the water. Now what's going to happen? Hopefully you can expect that the temperature of the unknown metal will go down and the temperature of the water will go up, and they'll reach some constant equilibrium temperature after the heat has been exchanged. So whatever that heat is that was lost by the metal will be gained by the water, and we can use that to our advantage to figure out what that unknown metal is. All right, the flow of heat stops only when the temperature is the same. So if the final temperature is 29.3 degrees Celsius, solve for the heat capacity of the metal. All right, so let's think this through. Assuming no heat is lost, then heat gained is equal to heat lost. Let's calculate the heat gained by the water first. So we know its heat capacity, 4.184. It's a mass of 125 and temperature change of about 4.3 degrees. Oops, 3.7. You get 1900 joules gained by the water. So that must equal the heat lost by the metal. So the Q of the metal is equal to negative 1900 joules, which is the same equation, different numbers. So negative 1900 joules, you arrange it and solve for heat capacity. So substitute the grams and the temperature change, and you should get that's 0.44 joules per gram degree Celsius. If you look on the chart, you can see that that was probably another chunk of iron, because it's got 0.449 for the known specific heat capacity of iron. All right. All right. Next, let's talk about energy and the change of state. During a change of state, energy is absorbed or released, but no temperature change is observed. You saw with boiling water and with freezing ice, unless if you don't have salt, that the change is, there is no more change once there's a change of state going on. So that would show up in a graph like this. If you have temperature versus amount of heat added. If you had some ice, you'd heat it up to 0, and then you wouldn't have any temperature change for a while as you're adding heat, and it was melting. Once it's all melted, then it can start absorbing heat again till it starts boiling. It'll absorb heat, notice a lot more heat, until it's all evaporated, and then the steam can be heated up. So this represents the change of temperature versus heat added for water going through phase changes. So if you want to calculate those energy changes, you would have to know something about how to calculate the Q values during a phase change. There's no temperature change, so we can't use the equation that we had. So for freezing, the energy needed to freeze or melt a substance is equal to the moles of the substance times the heat of fusion. Okay, looks a bit like the freezing point depression calculation. The heat of fusion is 6.01 kilojoules per mole of water. For boiling, same equation, but it needs a lot more energy to boil, which should make sense. Gases have a lot more energy than liquids. So to freeze, you need 6 kilojoules per mole of water. That would be released to freeze or absorbed to melt. And to vaporize, you need 40.7 kilojoules absorbed to evaporate or released when you condense. So let's calculate. How much heat would be released when 10 grams of water would freeze? So first you have to find moles, because that's what the heat of fusion is calculated in, moles per degree. And then you multiply it by the kilojoules per mole. Mole. That's the heat of fusion. You get 6 kilojoules released for every mole of water frozen. So it's negative 3.34 kilojoules. All right, so let's think through the whole process of absorbing heat, melting, and then warming up again. So if we have some ice at 0, we have 20 grams. How much energy will it take to first melt it and then to warm it up? So first calculate how much energy it would take to melt it. That's the Q of fusion. Then take that 20 grams and calculate how much it would take to warm it up. And then add those numbers together for the total amount of energy. Now be careful, because the Q of fusion will end up with kilojoules and Q of warming will end up with joules. So you're going to have to rectify that before you put the two together. So when you add them together, you get 8.76 kilojoules. Give that a try and ask me for help in class if you have trouble, but just plug in the numbers and see what you can do. All right, that's as much as we're going to do today. Have a lovely evening. See you soon. Bye.